I do want to talk about the Buffon's Needle project that we just did, because there's something really interesting in that what Buffon discovered. So I've actually have a simulation running right now. So let me put this up on the screen. Can I show you what I'm looking at right here? I've got a simulation running that is slowly dropping little needles onto a paper and keeping track of how many dropped and how many land on the line. Now, it'll get faster and faster here and start dropping more. But you can see right now it's around 2.9, 2.85, 2.8, 2.8, 2.93, 304. But the more it drops, the closer that calculation gets to a particular number. Oh, now it's really dropping a lot on there. It's hanging around 2.8 right now. We're up over 500 dropped. 750 dropped. We're at 2.9. And it's just going and going here. Oh, now we're right at 3 after dropping 1,000. The numbers seems to be slowly getting a little bit larger. Nope, not back down to 2.9. Just leaving that simulation running there. But it's interesting what Buffon found is the more and more and more you drop and doing this calculation, it's still dropping, but the picture quit dropping. But you see the math still up there. It's just not showing it anymore. It's about 3.02. Oh, now it's catching up. It did the math, and now it's got to catch up with the. There we go. Start it up again. There's several of these you can find on the internet. Here's one. I don't like that one. I'm going to go up to this one. There's the one I like. So this one, let's just drop 1. So it drops 1. Or I can drop 10 at a time. And it keeps the running total down here. I can drop 100 at a time. I can drop 1,000 at a time. And it's keeping the number right down here at the bottom of the screen. The number of drops divided by the number of hits. And it's at 3.09. If I just keep dropping 1,000, 3.10, 3.13, 3.10, 3.07. It's starting to get very consistent. The larger numbers get. We've dropped 11,000 needles, and 3,520 of them have landed on the line. Drop, drop, drop. Over 20,000. 30,000. Look at 30,000 needles. It's at 3.1417988. Basically, what Buffon discovered is that the more and more and more and more you drop, the closer that ratio gets to pi. Pi is 3.1415. And this is 179. We're very, very close to pi for the first 5 digits. And it all has to do with, if you do the math, and it's some pretty high level math in there, the probability and the calculations of the links, how far the lines are apart, how long the needles are, it all comes down to pi because of the rotation of that needle. You think you can rotate that needle around 180, 360 degrees, and it makes a circle. But the more and more you drop, the closer it gets to pi, because it all has to do with that rotation of the needle that makes a circle. So that's the unknown factor in there that makes this so weird, that it gets really, really close. Let's go back to our simulation over here that's dropping. See, it's getting closer and closer to pi the more we dropped. When we started out, it was like at 2.5 and 2.9, but now it's getting closer and closer the more it's dropped. It's almost dropped 3,000 now, and it's 3.08, 307, goes down a little bit to 6 occasionally, but it gets closer and closer to that 3.14159. So anyway, this Buffon's Needle project, the more and more you drop, the closer that gets to pi, which is really weird, but it has to do with the rotation of that needle. And as you rotate it around, it's to be the shape of a circle. If you rotate it 360 degrees, and the circle is calculated with pi, when you talk about the perimeter or the area, circumference, whatever, that factors into the math when you use the probability and the distances and do all the math. Pi comes into that because the needle could be rotated 360 degrees. So the more and more you drop, as this simulation shows, it approaches pi. This one over here that we did ourselves, we dropped 30,000 needles, and that ratio of drops divided by hits is at 3.14179. That's pretty good. That's really good. So I did kind of put our numbers together, and we're at 3.5, combining everyone's in the class. 3.5, but we've only dropped like 1,000 total. The more you drop, the closer you get to 3.14. Pretty interesting the way that math works with the real world. Oh, the graphics stopped again. It's going to have to catch up. 3.08. All right. So just wanted to show you Buffon's needle. It's kind of a little quirky. Oh, we're at 3.1. Little quirky thing in math. There's lots of things like this in math that it's amazing how things in real life tie in mathematically. We're at 3.13. See, it's getting real close now. It's 7,000. So we're going to stop there. Let's go look and see what this week's is. 0B. Here we are. We're down here. So if you haven't done this Buffon's needle project, do that. It's easy points. Easy points. If you need to go back and look at last week's video, but make sure you get that done. If we go down here and see Buffon's needle project, 50 out of 50, it's a 50-point assignment. So it'll help your grade a lot by getting an easy 50 points. And this week is a 50-point assignment, the golden ratio assignment. So again, we're doing a project again this week. So let me go and see what it has in Buzz. It doesn't have much in Buzz because we are going to talk about it ourselves. We're going to be reviewing this in class. So all I have on here is this. So let me switch over to my slideshow. All right, this is what we're going to look at. And I want you to look at this, and I'm going to set up a poll real quick here. So you can use the little poll feature down by the chat, the diamond square, the triangle, square, circle thing. I'm going to start a poll. Look at these rectangles and say which rectangle looks like it's the correct way to draw a rectangle. What I mean by that is like which one of those is appealing to you the most. Like if I was going to draw a rectangle, that's about the ratio I would draw it. Because some of these may look like, okay, that's a weird looking rectangle. It's way too long, or that one's way too short. But which one to you is the correct triangle? Which one just looks the most pleasing? And I'm going to put up a poll here. Let me set this up real quick. I didn't have it set up. All right, I've launched the poll. So go to the little poll thing and enter your vote. Madison likes G, she says. Click on the little triangle, square, circle thing where the poll is. It should be somewhere near the chat. And you can enter your vote on which one you think is most pleasing to the eye, just the right one. F is getting some love there. F got some love yesterday in my class too. F and G were kind of like the ones in the middle, it appears. All right. And I think next year I'm going to rearrange these just to see if it makes a difference which ones are in the middle and which ones are not. Just because I think it's interesting just to take this poll. All right, I'm going to move on here. I want to talk about Fibonacci sequence. You may have heard of this. You may not have heard of this. But there's a sequence of numbers, and here's the beginning of it. 1, 1, 2, 3, 5, 8, 13. This is known as the Fibonacci sequence. Very famous in math. And Fibonacci was an Italian mathematician. That was not his name, but that's the name he published this under. And look, he lived from 1170 to 1240. So he lived like 800 years ago. He promoted the Hindu Arabic number system in Europe, which is a lot of the numbers we use today, the characters we use for the numbers. He worked on algebra. And this his real name was Leonardo of Pisa. And he lived at the time they were building the Tower of Pisa, which we now know as the Leaning Tower of Pisa. It wasn't leaning when they built it, but it's leaning now. But that's when the Tower of Pisa was built, when he was a young man, as a young boy. But this sequence, and you can continue this sequence forever. We've looked at sequences, arithmetic sequences, geometric sequences, but this sequence is a little different. Let me show you how it works. So with this sequence, you start with the two ones, and you add the two ones together to get 2. So you always add the last two numbers together to get the next number. So 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. And it continues on forever. 144 plus 233 is 377. 233 plus 377 is 610. And the sequence goes on and on and on. And this is known as the Fibonacci sequence. Now, Fibonacci is actually an Italian word that means a fool. Everyone thought this was foolish when he was doing this whole sequence, and that's just foolish. It's not good for anything. What in the world are you talking about? What are you, some kind of moron? And so he published it under the name Fibonacci, which was a fool, because he thought, hey, there's something to this, and I'm going to publish it anyway. So he published this sequence, and we started looking at the sequence of the last 800 years. And one thing we noticed with the sequence is if we take those numbers and we make boxes, like squares, right? A square that's 1 by 1. So let's start with a 1 by 1 square. And then the second number is also a 1. So another 1 by 1 square, and then a 2 by 2 square, and then a 3 by 3 square. And then the next number is 5. So you do a 5 by 5 square, and it fits right next to the other boxes every time. 8 by 8 square, 13 by 13 square, 21 by 21 square. And you notice it's making rectangles. When it adds that box on the side, it makes a rectangle. So finally, we have this great big rectangle. If you look at the outside shape of this great big rectangle. This one's an up and down rectangle, right? Then you have this rectangle up here. But every time you add this square onto the side, it creates a new rectangle. And all of those rectangles have the same ratio of width to length. If you divide the length, how long it is, by the height, it's always the same ratio. And this has become known as the golden rectangle because, and there have been many, many studies for this shape of rectangle is the most pleasing to the eye. Weird. Most pleasing to the eye. We like this ratio. We like this length compared to this height. And with these, there's also something known as the golden spiral. If we start in the very smallest squares in there and we connect all the diagonal corners, and don't connect them with a straight line, let's connect them with a curved line so we can make a spiral. So look at this. We start red right there in the middle. You connect to the next corner, then to the next square. You just keep making this spiral that goes out through each of the corners, spirals out as it goes. Since it's based on the golden rectangle, this is known as the golden spiral. And you're like, okay, is that the most pleasing spiral? I don't know. We don't really study pleasing spirals, but this spiral is everywhere. This is found in nature all over the place. It is a pleasing spiral to us because it's based on those same ratios, those same proportions as the golden rectangle. So if you take the 5 by, let's each one of those squares and we figure the area, right? So the 5 by 5, it's 5 blocks wide, it's 5 blocks high. So it has an area of 25, right? We know that 5 times 5 is the area of the rectangle. It's 25. If it's an 8 by 8, we know that's 64. So if we go back to these squares and said, let's look at the areas, because that's a 2 by 2, a 3 by 3, 5 by 5, 8 by 8, all of those. Oh, here's that golden spiral. And we'll put the areas in there. We're not going to put them all, but there's area of 1, area of 4, area of 9, area of 25, because we're just doing the 3 by 3, 5 by 5. The next will be area 64, and so on and so forth. If we look at those numbers, and let's take a look at those numbers here. Oh, come on. There we go. They all have the same ratio. The areas have the same ratio. If we take 144 and divide it by 89, we get 1.618. And if we take the 89 and divide 144 into it, we get 0.618. And this ratio, the higher we go, the closer this is, the more decimals it adds, 1.61, and it'll continue on. But there's a certain ratio, just a little bit larger than 1.6, that apparently is very appealing and very sound, and it's just found all over the place. So D is actually the rectangle that is closest to that. We like the ones just a little bit longer, which is fine. We're still in the same ballpark. Nobody likes the really long J or I. Those just seem too long to us. A, B, those seem too close to a square. We like the ones in the middle. Now, here's the interesting thing about this Fibonacci sequence. Like I said, it's found all around us. Look at a tree. And most trees, not every tree necessarily, but most trees will follow the Fibonacci sequence. It'll have one branch, and then 2, and then 3, and then 5, and then 8, and then 13 as you section off heights of the tree. So nature seems to be fun. Like I say, Fibonacci did not create this sequence. He discovered it because it exists in nature. So the pattern of branching is repeated for each of the new stems. Says a good example is the sneeze wort. I guess if you see a sneeze wort tree, it's going to follow this almost religiously. And root systems. Going down, roots will also develop the same type of pattern. Let's look at this. The Mona Lisa, one of the most famous paintings in the world. If you take that golden spiral and place it over the Mona Lisa, her proportions of her face and her head and all of that fit nicely in this golden spiral. Look at that, from her chin to the top of her head, just fits nicely into that golden rectangle, into that golden spiral as far as the height and all of that. And it's like, maybe that's how it became the most famous painting in the world, because it proportionally, mathematically is appealing. Mathematically. Let's look at this. Going back thousands of years ago in Greece, the Pantheon. Look, they built this before the Fibonacci sequence even existed, right? And it fits this golden rectangle pattern. The height of the Pantheon compared to the width is that same golden ratio of the length to the height. And sections of it also kind of fit in there. It's really, really interesting how architecture oftentimes is built for that golden ratio that we like. If you take this nautilus shell and you cut it open where you can see the inside of it, look how closely that follows that spiral, especially in the middle as it's coming out. It has that very similar spiral that we see as the golden spiral. This I really think is fascinating. The average human ear is almost a perfect golden spiral that follows this Fibonacci sequence and this ratio. Butterflies, here's this monarch butterfly, and the wings are like almost a perfect spiral in there. This is great. Hurricanes, galaxies, the big things in nature. You could take that spiral and overlay that onto these hurricanes when they put them up in the weather map, and it almost folds it perfectly. So this sequence isn't just something that Fibonacci created. This is something he discovered because nature follows this sequence. When we apply and draw this spiral using the area of that sequence, those ratios is found in lots of places. Galaxies even. So that's just amazing. So there's something in physics that mathematically works. This is a naturally occurring sequence of numbers that you find in the scientific world. Here's the one that really got me. Let's look at your DNA. If you take right here at the bottom the height of your DNA, and For the width, let's take one full cycle, one full loop. This is at the bottom. It goes up, it comes back down. So we'll consider that one full cycle of your DNA strand. And if you take that length and divide it by that height, it's 1.618. It's built into our very DNA, this Fibonacci sequence, this ratio that's derived from that sequence is built into our very DNA. So no wonder it occurs in nature. It's part of everything. It's found all over the place. Pretty cool. So with that, here's your assignment for the week. You're going to need a tape measure, a ruler, or something. I want you to take pictures of 3 things that you can find, either around your house or in your community. Even online, you can find like logos that represent a golden rectangle. Or if you find a golden spiral, that's cool too. It can be items in nature. It can be architecture. It can be logos. It can be art. If you find golden rectangles, submit the pictures. Notice the red along with the measurements to show that it represents the golden ratio approximately, about 1.6. It's not going to be perfect. About 1.6. And pictures of golden spirals, you don't need any measurements of the spiral. If it looks very similar to that spiral, we're going to assume it's close enough. Okay. So that's what you're turning in. Go to like a Google Doc. You're going to do 3 pictures. 3 pictures along with the measurements, unless they're spirals. And that's what you're turning in this week. Now, I want to show you something. Advertisers understand the golden ratio. Advertisers understand this. Put this ruler here. Advertisers know this. Let me look at this. Here's my debit card. All right. And I'm going to pull up a calculator. All right. So here's our calculator. So I'm going to take my debit card and I'm going to see exactly how long is this in millimeters. All right. So let's turn it that way. This is, get this straight, 85 millimeters long. Because that's not really straight for you guys, but 85. 85. And I'm going to divide that by the height of my debit card, which is 53. 53. If I divide 85 by 53, look at there, 1.603. Debit cards, credit cards are that golden rectangle. It appeals to us. That's not an accident. Lots of marketing people study these dimensions and they want the most appealing products. You can find lots of company logos that will be the height and length, or short, taller and wide, that will have that 1.6 ratio to them. Company logos will have that. It's crazy. The Fibonacci sequence itself, the 1, 1, 2, 3, 5, 8, 13, you can find a lot of flowers that follow that. It'll have 5 petals, it'll have 8 petals, it'll have 13 petals, it'll have 21 petals. Different flowers follow that same sequence number. The seeds in the middle of some of these, some of them have that spiral and the seeds in the middle of the flowers. It's everywhere. We are surrounded by math and it's consistent and it's there. So have fun with this. This is our last project of the year. Like I say, it's 50 points. This one and last week's together is like a test grade. I'm trying to give you an easy boost right here at the end of the semester. So get 3 pictures, turn those in, do the measurements to show it's about a 1.6, like this was a 1.6. Find things that fit. Not every rectangle fits that for sure. Not everything does, but there's a lot. There's a lot out there. So have fun with that. Just wanted you to see some things where math really is life. You can't really separate it because it's just built into nature. The hurricane thing fascinates me, that it fits that golden spiral so amazingly. So, okay, that's all I got for you. If you don't have any questions, have a great summer. If I don't see you again, I will be emailing out exemptions on Friday for finals. So hopefully you're exempt, and this will be the last time I see you. This is an A day, so I only have class again on Thursday. If you have questions, come by on Thursday, and we'll get that worked out. I don't know that anyone here is below 70. I don't think anyone here is, so I don't know that anyone's going to be required to be here. No, none of you guys are below 70 there. So, yeah, none of you have to be here Thursday. But if you have to take the final, it'll be available Tuesday morning at midnight. It'll close Thursday at 11 a.m. If you, I got to remember this. If you have to take the final, if you're not exempt, then you need to be in class next week. I will see you. I posted the exam schedule in the front page of our Google Classroom, and this class will meet Thursday morning at 7:15. Now, the plan is if you have to take the final, you'll come Thursday morning, 7:15. I'll go, yep, you've taken the final. Have a great summer. Goodbye. But if you come and you have not taken the final, I'll say, okay, take the final now in class, because that's what the class is for, the final. Because it's due at 11, and we meet it that morning. Notice the time is different. No, it's not. No, the time is the same, 7:15. So, but hopefully most of you be exempt. If not, get the final taken quickly. Don't wait till Thursday morning. All right. Any questions? Hang around. Otherwise, it was nice seeing you guys. Have a great summer if I don't see you again.
No! Give me the baby! No! Give me! It's mine! It's mine! My baby!